In this video, we will know about the standard subgroups of a group G, namely normalizer of A, where A is an element of the given group G, normalizer of H is a subgroup of G, and center of G, and commutator subgroup of G, and all that with an example. So if A belongs to G, then N of A, which is the collection of all elements in G which commute with A. Okay, so this is what we are going to show as a subgroup of G. This is called normalizer of A. And if H is a subgroup of G, then normalizer of H is all those elements of G which satisfy this condition, XH is equal to HX. So that is also a subgroup of G that we are going to establish. And the center of G, which is denoted as Z of G, which is those elements of G which commute with all the elements of G. So N of A is just those elements which commute with A only, but this is those elements which commute with all the elements of G. So we are going to show that this is also a subgroup of G, and the description of commutator subgroup is also given, and we are going to have an example from a non-abelian group, namely S3. So first we will establish that N of A is a subgroup of G. So if A belongs to G, then N of A, which is this collection, is a subgroup of G. So when you write the proof, even if this is not given in the question, you are supposed to write what that N of A is. So it is all those X in G which commute with A. So this has to be written, and then only you have to proceed. Now whenever we try to prove a subcollection to be a subgroup, first of all we have to show that it is non-empty. A non-empty subset, we can check whether it is a subgroup or not. So not to show that it is non-empty, we have to produce an element. So obvious element is the identity element of G which is present in N of A, because E commutes with A. E commutes with all the elements. In particular, if it commutes with A only, it can be present in N of A. If any element has to be in N of A, it has to commute with A. So because E into A is same as A into E, we have our E belonging to N of A. So N of A is non-empty. So we make use of this GPTC, this rule we use. So what is given? N of A alone is given. So what we are trying to prove is non-empty, and it's a subgroup. For subgroup, we have to use this criterion. For XY belonging to N of A, we have to show that XY inverse is also in N of A. So that is what we have claimed. XY inverse commute with A. If only this XY inverse commutes with A, it can be present in N of A. So this is what we are trying to establish. Now you consider X and Y in N of A. Because X is in N of A, you have XA is equal to AX and YA is equal to AY. From here, retain Y, post multiply both sides by A inverse, so you get this, and find Y inverse, and that is, you have to have it in the reverse order. A dot B, the whole inverse, is B inverse A inverse. So you have A inverse, the whole inverse, that is A, then Y inverse, and then A inverse. Name this as equation 2, and this has to be named as equation 1. Now this is what we have to establish, for which we consider this XY inverse A. And replace, we use associativity so that we can write X Y inverse A, or even just replace your Y inverse by 2 like this, and then associativity is used so that you have this step, and this one A inverse A is E. So this becomes just X A Y inverse, and again when we consider equation 1, this XA can be rewritten as AX. Again associativity can be used to get this step. So this is XY inverse A, and this is A XY inverse. So as xy inverse commutes with A, it has to be a member of N of A. So we have N of A to be a subgroup of G. So what is given we have written, and what is to be proved, all these come under N of A is a subgroup. We haven't written explicitly, but N of A is a subgroup is what is to be proved. So all these come under technique part, and this is the conclusion. So remember that GPTC rule. Now in the second one, if H is a subgroup of G, then N of H, which is this collection, is a subgroup of G, for which what is given you have written. Now we have to, as before, it should be non-empty collection. So E commutes, E being a member of H, HE will be equal to H. So you have H is also equal to EH. So HE is equal to EH, and therefore that E must be present in N of H. Now to prove that N of H is a subgroup, we have to consider two elements x and y in N of H and show that xy inverse belongs to N of H. But any element will be in N of H provided xy inverse. That is, here we want to show xy inverse to be a member of N of H. So we have to show that xy inverse H is equal to H xy inverse, and that is what is written here. So because we have assumed x and y to be in N of H, we have to have, by the definition of N of H, these two steps. And in this, we consider y inverse H. If we consider y inverse H, then we have that to be HY inverse. So when we consider XY inverse H, we make use of this to get XY inverse H to be HXY inverse. So by the definition of N of H, we have XY inverse belonging to N of H. And therefore, N of H is a subgroup of G. So here again, we have proceeded to have the proof by having this in our mind, GPTC rule. What is given? Only this is given. What is to be proved? It is a subgroup. So these are the techniques, non-empty, and then xy inverse belongs to N of H whenever xy belongs to N of H, and then conclusion. Next is the center of G, which is all those elements which commute, all those elements of G which commute with all the elements of G. The students write this for every G in G out of the bracket. It has to be written within the bracket only. So this is a subgroup of G. Now you consider Z of G. What is given you have to write. So this is what is given. So even in the question, if this is not given, only you are asked to show that Z of G is a subgroup of G. When you write the answer, first you have to describe what is that Z of G. So now we have to prove that this is a subgroup, for which it has to be non-empty, and again E is the element which commutes with all the elements of G, and therefore we have E to be a member of Z of G. Next we shall consider x, y in G, x comma y in G, Z of G, and I have to show that xy inverse belongs to Z of G. That means this element also commutes with all the elements of G. Now because x is in Z of G, by the definition of Z of G, you have xg is equal to gx, name that as 1, and similarly yg is equal to gy. All these are true for all G in G, and this is post multiplying both sides by G inverse, you have this, and then finding y inverse. In the case of N of A, we proceeded like this. So in the same way we have this step, G y inverse, G inverse. Now you consider xy inverse G and replace your y inverse from 2 by this. So you have this. Now using associativity, you can group the terms like this. G inverse G is of course E, and this xg is nothing but gx by 1. Xg is nothing but gx, so you have this. Again use associativity to get this step. So xy inverse commutes with G for all G, and therefore xy inverse should belong to Z of G. Hence Z of G is a subgroup of G. Now we have the definition of commutator subgroup. of a given group G. So let G be the given group, and you consider two elements A and B in G, then the commutator of A and B is the element A, B, A inverse, B inverse. So you have the product of these four, first A, B, A inverse, B inverse. So that is an element, another element, and then the first element's inverse, the second element's inverse. Now if A and B commute, then this will be just E. That's very obvious. And now how this G prime, the commutator subgroup, that is defined. So in terms of this commutator, in fact it is described as the smallest subgroup generated by the set of commutator elements. That is one way of defining that. The other way of defining commutator subgroup is this. So it is the product of these elements where each one is a commutator. Each xi is a commutator in G. That means each xi is of this form: A, B, A inverse, B inverse. So in other words, G prime is the finite product of commutators in G. So it is this definition which helps us in proving that this is a commutator subgroup. In words we have written, so that will be recalled. So if G is any group, then G prime is a subgroup of G. So what is given? G is a given group, any group. Now we have to prove that G prime, that is described in this way already, is a subgroup of G. Now what is the technique involved? First we notice that this is non-empty. So you have how many ever times that you write, again you get only E. So G prime is non-empty, and of course it contains the identity element, namely E. Now if C and D are in, this is actually G prime. If C and D are in G prime, then we have C being written as x1 to xn, the product it is, and similarly D is y1 to ym, the product, where each xi and yj is a commutator in G. Now you consider C into D. So we closure and existence of inverse. That criterion is used to prove that G prime is a subgroup of G. So CD, when we consider what is C, that's written, and what is D, that's written by its side. Each one, see, this is a commutator, this is a commutator, so product of commutators, again product of commutators, the whole lot is a product of commutators. So it is a finite product of commutators. So by the definition of G prime, it should be there in G prime. Now you consider C inverse. So C is this, so its inverse is given by this. We know that A dot B, the whole inverse is B inverse, A inverse. So the inverse is written in the reverse order, and each xi is a commutator. So xi inverse, when we consider, this is what we have. So that is also a commutator. So what will happen because of this? Your C inverse is a finite product of commutators and therefore should belong to G prime. So both CD and C inverse are present in G prime, therefore G prime is a subgroup of G. Now in the next we are going to have, if H and K are subgroups of a group G, then H intersection K is also a subgroup, but H union K is not a subgroup. Now we consider H intersection K, and we notice that it is non-empty because E belongs to both H as well as K. Now to show that it is subgroup, first we have established that it is non-empty. Then we'll have to show that for two elements xy in H intersection K, x dot y inverse also belongs to H intersection K. So how that is established? Now if x and y are in the intersection, it should be present in H as well as in K. So that is what is written here. Now since H and K are subgroups of G, x dot y inverse is also a member of H because H is a subgroup. And similarly it belongs to K also. So it must be there in the intersection. As it is belonging to both H and K, it should be there in the intersection. So that proves that H intersection K is a subgroup of G. Now we notice that H union K need not be a subgroup. So whenever something is not true, that is established by producing a counter example. So in S3, S3 is the collection epsilon, alpha, beta, gamma, delta, theta, and its table is given here. If H is this subgroup, we know already that it has got 4 proper subgroups. Of the 4, we shall consider H to be this subgroup and K to be this subgroup. The union, when we consider, it will have these many elements, epsilon, alpha, beta. But that is not a group as it is not closed. Why? When we consider alpha with alpha, epsilon present. Beta with beta, epsilon present. But alpha with beta, when we consider alpha with beta, it is delta that is not present in the collection. And similarly, when you consider beta with alpha, it is theta that is also not present. So closure fails. So by the criterion for any non-empty subset to be a subgroup, we cannot have H union K to be a subgroup because closure fails. Now, to illustrate the normalizer of an element, normalizer of a subgroup, commutator subgroup, and center of G, let us consider this example S3. We know pretty well that H1, that is H1, H2, H3, H4 are the 4 proper subgroups of S3. So whenever you give S3 to be an example, you have to mention what these stand for. And if it inverts subgroups means, you can list the subgroups like this. Now we consider N of A. We have to compute what this N of A for each and every element of S3. So it is all those elements which commute with A. So that is the elements present in N of A. So N of epsilon, all those elements which commute with epsilon. So all the elements of S3 will commute with epsilon because that is identity element. So you have your N of epsilon to be the whole of S3. Next, if we consider N of alpha, it is all those elements of S3 which commutes with alpha. So, but from the table you can see that we cannot have in the place of X beta because beta alpha is theta and alpha beta is delta. So they are not the same. So that means N of alpha will consist of only, similarly with the other elements we can check from the table and we can conclude that this N of alpha is just epsilon alpha and that is your H1. We know already that N of A is a subgroup and H1 is also a subgroup we know. And it so happens that in this case it is H1. Similarly, when we compute N of beta, we can have it as H2, N of gamma, H3, N of delta and theta to be H4. Procedure is the same. You have to make use of the table. Now, the definition of N of H is known to us already. So, in this case, only alpha epsilon and alpha will satisfy this condition. So, you have N of H1 to be H1 and similarly N of H2 to be H2, N of H3 to be H3, N of H4 to be the whole of S3. Because H4 later you will come across the concept of right coset, left coset and normal subgroup. So only for a normal subgroup, every left coset will be a right coset. This is right coset and this is left coset. So N of H4 will be the whole of S3. And in this case, this is not abelian. So Z of G is just singleton epsilon. Then to find the commutator subgroup, we compute A, B, A inverse, B inverse. You have to consider a pair of elements from this collection S3. So if you have considered alpha and beta, this is what we get. Alpha inverse is alpha. Alpha inverse is alpha. So beta inverse in the same way is beta. But alpha beta is delta. Alpha beta is delta. So delta conversion delta theta. And similarly, when you consider B to be gamma, A to be alpha, on computation you get that to be delta. So when we consider G prime, it will be, see, we will have it as, we have already said that G prime is the product of, finite product of its commutators. So when we compute this, we will have that either to be epsilon or to be theta or to be delta. So when you consider the finite product, that will have elements as singleton epsilon, delta, theta, and we know that that is nothing but our H4. Now we notice this, so it's given as a word of caution that if the given group G is non-abelian in determining at least one proper subgroup of G, because sometimes you may be given your assignment, some group will be given in the tabular form, that is Cayley table. Then from that you may have to infer so many concepts. So I mean you have to check too many conditions to have the solution of the question asked in the assignment. So for which this discussion can be used. That is, just now we proved that n of a, n of h, z of g and g prime are all subgroups. So if the given group is non-abelian, then to find one of the subgroups, this concept can be used. But if the group is abelian or cyclic, then n of a or n of h or z of g or g prime will either be g or singleton e. So in such cases, the subgroups need to be computed. So proper subgroups, if we want to find, then there is no other go, we'll have to compute it. So how that could be done, that will be discussed in our next video, which will be titled as Properties of Cyclic Groups. So here is a collection G consisting of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and operation on G is defined in this way. Given A and B in G, you consider A plus B to be A plus B minus 4 mod 10. You compute this. After that, you add the resultant with 2. So that is how we apply the operation on G. When we consider the Cayley table, it will look like this. Now in this, when you can easily see that it's an abelian group. So when you compute your normalizer of an element or subgroup or commutator subgroup, you will have them to be trivial. That is, you will have it as either singleton E or G itself. But when you actually, I mean, that doesn't mean that it does not have any proper subgroup. So we'll have to compute. And for that, this is a cyclic group that can be checked by considering 2 as the identity element, and you have to check whether 3 is a generator. Even if you find one generator, from the properties of cyclic groups, you can know that how we can consider the other generators. So then again, actual computation should only be carried out to find whether you have other subgroups. So this definitely has, being a finite cyclic group, converse of Lagrange's theorem will be true. So all that all those concepts will be dealt later after finishing our properties of cyclic groups. So have this in your mind, and you can have the solution, and that can be given in the comment section, maybe after seeing the next video on properties of cyclic groups. So I am eagerly